Welcome back to the deep dive. We're here to unpack the complex stuff and, really pull out what matters. Today, we're tackling something pretty fundamental in AI, making language models, LMs, genuinely smarter, not just capable, but actually better at reasoning for complex, multi-step problems. Because for a while now, LMs have been, well, a bit like star students facing a surprise test. They do amazing things, sure, but learning truly new, complex skills from scratch, especially using reinforcement learning, RL. That's tough. They hit this big wall called the exploration challenge. Think of it like this: trying to learn swimming, but you only hear you drowned or perfect swim. Nothing in between.
Right.
Yeah, no feedback on like how you're kicking or moving your arms. It's just super sparse feedback, all or nothing, which means often these LMs need to be pretty good already just to stumble onto any kind of useful feedback. It really bottlenecks real learning.
That's a great way to put it. And that exact problem, that sparsity, has really pushed the field towards something called distillation. This is where you use these, well, often enormous LMs, the ones that are already great problem solvers, to act as teachers for smaller, more nimble student models. But here's the catch. These big models are good at solving, but they weren't built to teach. Their raw thinking often needs a lot of manual cleanup post-processing to make it actually useful as a lesson.
Right. It's not naturally instructional. It's just their raw output.
Exactly. And that cleanup, it's another step, often costly, and honestly, sometimes more art than science.
Okay, and this is where today's topic really comes into focus, right? This new idea, reinforcement learned teachers, or RLTs. You're saying this changes the whole dynamic, moves LMs from just solvers to actual educators.
Precisely. It's a fundamental shift. Our mission today is to really unpack how these RLTs get around those old limitations and what this could mean going forward.
All right, let's dive into that core innovation. How does it work?
Okay, so traditionally, RL for LMs goes something like this.
Yeah.
Here's a problem, now think, and give you the solution, all from scratch.
Right. Solve this complex math problem. Go.
Yeah. The big idea, the sort of academic twist with RLTs, is completely different. It feels almost counterintuitive at first. An RLT isn't asked to find an answer it doesn't already have. Instead, you give it both the question and the ground truth, the correct solution.
Both. Okay, so what is its job then?
Its job is to connect the dots, to generate the detailed, step-by-step explanation of how you get from the question to that known solution.
Ah, I see. So it's not about finding the destination, but explaining the journey.
Exactly. Like a human teacher who knows the answer and focuses purely on explaining the process, breaking it down.
That sounds much more manageable. It neatly avoids that drowned or swimming perfectly problem, doesn't it? Because the answer is always there as a reference point.
Precisely. Academically, it's quite elegant because it just sidesteps that whole exploration nightmare. The RLT always has the solution. So it can get continuous, really dense feedback on the quality of its explanation, not just a sparse yes-no on a final answer it struggled to find.
Dense feedback on the explanation itself.
Yeah. It's rethinking the goal for the LM in RL. Not solve this, but teach how to solve this. We're teaching the model how to teach.
Okay. Now, you mentioned the reward function. This is where the teaching part really gets defined, you said. Rewarding not just correctness, but teachability. What's the academic magic there?
Right, this is the absolute core of it. The reward function is carefully built with two key pieces. First, there's RSS. That stands for Student Understanding of Solutions.
Students' understanding.
This part measures how well a separate student LM, usually a smaller one, can understand the RLT's explanation and then correctly reconstruct the solution from that explanation. It looks at the student's log probabilities for the solution tokens.
Log probabilities. So, like, how confident the student model is in predicting each part of the answer based on the explanation it just saw.
Exactly that.
Yeah.
And crucially, it looks at both the average confidence and the minimum confidence across all parts of the solution.
Minimum. Why the minimum?
Because if the explanation is great for 99% of the answer, but totally fails on one critical step, the student might still get it wrong. The minimum ensures every step is clearly explained. No weak links allowed. It forces the RLT to be thorough, clear, comprehensive in getting the student to the answer. That's the goal. Clarity and effectiveness.
Got it. So RSS ensures the explanation actually leads the student to the right place. Makes sense. What's the other piece? You said there were two.
The second part is RKL. This focuses on the interpretability of explanations. And this, I think, is where the real cleverness for logical coherence comes in.
Interpretability. How logical the steps are. Sort of. It uses KL divergence. Now, KL divergence sounds technical, but think of it as measuring how surprising one set of probabilities is compared to another. Here, RKL checks if the think tokens, the actual explanatory steps from the RLT, seem like natural, logical steps that the student might have thought of given only the original question and its own knowledge.
Ah, okay. So the RLT sees the question A and D solution to make the explanation.
Yes.
But this RKL checks if those explanation steps make sense without knowing the solution beforehand, just based on the question.
Precisely. If the RLT includes steps that seem totally out of the blue to a student only seeing the question, it suggests the explanation might be, well, illogical, or maybe just repeating bits of the solution in disguise. It's like a cheat detector.
Yeah.
Without RKL, the RLT might learn weird shortcuts, like just repeating the answer slightly differently to boost the RSS score, or generating steps that don't actually teach anything useful.
So it's a regularizer. It keeps the explanation honest and actually instructive. Exactly. It ensures the explanation is a learnable, logical path, not just gibberish that happens to lead to the right answer sometimes. It forces the explanation to be understandable to an independent learner.
That's really smart. It's forcing the RLT to think like a good teacher would, building from what the student already knows.
That's the idea. Then these two parts are combined. RRLT equals RSS, RKL. That lambda is just a knob we can turn to balance how much we value the student getting the answer, RSS, versus how much we penalize illogical or uninterpretable steps, RKL.
So you tune it for the best balance.
Right. It creates this overall reward that pushes the RLT to generate explanations that are effective, logical, interpretable, and genuinely helpful from the student's point of view, truly teaching.
Okay, the academic thinking is clearly very clever, but does it actually work? What happens when you pit these RLTs against the current methods in the real world? Do we see actual performance gains?
We do. And the results are, frankly, quite striking, especially when you look at efficiency. One of the headline findings is that a relatively small RLT, just 7 billion parameters, using its raw output, no post-processing needed, actually performs better on really tough reasoning tasks than existing methods.
Better than what, specifically?
Better than complex distillation pipelines that often use much larger teacher models. We're talking hard benchmarks, competition math like AIM, graduate level stuff like math and GPQA. These need serious multi-step reasoning. And the baselines. They often rely on models like DeepSeek R1, which is enormous, 671 billion parameters. And even then, those baselines usually need that heavy manual post-processing we talked about to make the outputs usable for teaching.
Wow, so a 7B model straight out of the box is beating a process output from a model nearly 100 times its size.
That's what the results show. It's a huge leap in efficiency. Think about the compute savings, the faster development. It makes this kind of high-level reasoning much more accessible.
That really is democratizing, isn't it? You don't need a supercomputer cluster anymore.
Exactly. And it's not just for small students. These RLTs work well even when teaching much larger student models, like 32 billion parameter ones. Their explanations seem genuinely robust and transferable.
So the teaching quality holds up even for more capable students.
It seems so. Another big win is in cold starting traditional RL. Giving the RL process a good starting point.
Right, like giving it some good examples to learn from initially.
Yeah. The reasoning traces generated by RLTs turn out to be better starting points for further RL training than even the post-process traces from other RL teachers. You end up with better final performance.
So it accelerates the whole process and leads to a better outcome?
Correct. It's a more efficient path to high performance.
Okay, but the finding that really jumped out at me was this zero-shot out-of-domain transfer. That sounds potentially huge. What's going on there?
Ah, yes, that is truly fascinating.
Yeah.
It suggests something deeper is being learned. What it means is you train an RLT on one type of problem, say math and coding, and then you give it a problem from a completely different area, like the countdown task, which is more about logic and wordplay, without any extra training on that new task.
Yeah.
And it can still generate effective explanations. It transfers its teaching skill, zero shot.
Whoa. So it's not just learning math tricks, it's learning how to explain things more generally.
That's what it strongly suggests. It seems to be learning a more fundamental, domain-agnostic teaching ability. How to break things down, how to structure an explanation logically, regardless of the subject.
The potential applications of that.
Yeah.
An AI that can learn to teach across different fields.
Exactly. It's very exciting. And remember, all these gains, the performance, the cold start, the transfer, are achieved without that complex, often brittle, heuristic post-processing needed elsewhere.
Making it simpler and more efficient to deploy.
Absolutely. The training itself was done on, like, a single node with 8 high-end GPUs. Powerful, yes, but accessible to many labs, not just tech giants. And qualitatively, the feedback is that RLT explanations feel more grounded. Sometimes they even add extra verification steps you don't see from other models, and they avoid weird idiosyncratic phrasing. It just feels more like solid instruction.
Okay, so we've done the deep dive. We've seen the academic innovation, the impressive empirical results. Let's pull back a bit. What does this all mean for, everyone, for developers, for learners, for the future of AI?
I think the biggest implication is about access. RLTs have the potential to really democratize advanced AI reasoning. For a long time, getting models to do complex reasoning required these giant, often closed-source models, very expensive, very exclusive. By showing that smaller models can be trained to be excellent teachers, RLTs make these powerful capabilities much more accessible. Researchers, smaller companies, even educators could potentially leverage this. It lowers the barrier to entry.
Which could spur a lot more innovation across the board.
Definitely. And the research itself points to some really cool next steps.
Like what?
Well, imagine training the teacher and student together dynamically.
Mm.
The RLT adapts its explanations in real time based on how well the student is understanding. A truly personalized AI tutor.
Wow, okay. Like a live feedback loop between teacher and student.
Exactly.
Yeah.
Or even bolder, a single model that learns to be both the teacher and the student. It explains solutions it knows, then uses those explanations to teach itself how to solve problems from scratch.
A self-teaching, self-explaining AI.
It could potentially unify RL with supervised learning in a really powerful way. And of course, just scaling up bigger RLTs, more diverse training data, could unlock even more capability.
It really shifts the perspective, doesn't it? From AI as just a problem solver to AI as an educator and explainer. So here's something to think about. If these models can get so good at not just finding an answer, but explaining the how and the why in a way that's genuinely instructive, what does that tell us about teaching itself? And maybe more importantly for all of us, how might this change the way we end up learning from AI in the future? Moving beyond just getting answers to getting guided understanding, that's definitely something worth pondering.